a sphere is the set of all points in the space which are a fixed distance from a fixed point. So for instance, if we have given this fixed point P0 and we have given a certain distance r, so then the sphere will be all the points in the space, in the three-dimensional space that are this distance r from the point P0. So for instance, this point will be one point that satisfies this condition, but all the points that are in this circle will be also, but all the ones that are in all this surface will be also. So all these points in the surface here will satisfy the conditions that the distance from the point in the surface to P0 is always r. And this will be then the equation that the points have to satisfy, the points x, y, and z in the space have to satisfy in order to be in the sphere. So this equation comes from the distance between points, right? So we know how to calculate the distance between a generic point here, x, y, z, and the point P0, which is x0, y0, z0. Okay, so let's consider, for instance, this particular equation. So this is an equation of a sphere since it's of the form given before. So let's calculate in this sphere what is the radius, what is the fixed distance, and what is the center of this sphere. So first, the center of the sphere, the point P0, is going to be what is subtracted to the variables x, y, and z. In this case, it's going to be 1, 0, and 3. So the first component will be 1, the second component will be 0, and the third component here will be minus 3, since this last term here is actually z minus 3. And the distance then will come from the last coefficient here, that is r squared. So r will be the square root of whatever is there, and in this case is the square root of 5. So we calculate then what is the center of the sphere and what is the radius. Okay, another familiar surface is the cylinder, but the cylinder in mathematics is going to be much more general than what we normally understand by cylinder outside of mathematics, let's say. Normally a cylinder outside is something that looks like this. Well, this is will be a particular type of cylinder for us, but we are going to call cylinder any surface that is generated by moving a line. Like here, that we have this line that is moving, is getting all these places here parallelly around the circle. Well, it can be moved around any given curve. So for instance, if I have a curve like this, so then I have this line and I start moving this line all around this curve. Well, the surface that I obtain is also going to be called cylinder. So in that way, we could have a cylinder given by a parabola, for instance, and so that will be all the lines here and all the lines here. So all the surface that we go around will be then also called a cylinder. Or we can have also any base like this, and so we have vertical lines, and so this other surface is also going to be called a cylinder. Let's say, for instance, if we had given the equation of the parabola, like I drew before, that would be the equation of a parabola in the plane of the floor, let's say. So if we have a parabola given in here like this, so then the equation of the cylinder will be all the points that are in this parabola will be part of the cylinder, but also all the ones that are here with any value of z will be also part of the cylinder. So because of that, the equation of the cylinder is going to be just y equals 3x squared without the z equals 0, because z can take the value 0, or can take the value 1 or minus 1. Any value of z will give a point, x, y, z, that will be part of this cylinder. And in general, a surface defined by an algebraic equation of degree 2 will be called quadric. So this equation that we have written here, that are variables to degree 2, and so all the things that appear here are degree 2, and eventually degree 1 and degree 0. So an equation like this will define what is called a quadric. So a quadric is a generalization of the familiar conics. So you are familiar with ellipses, hyperbolas, and parabolas. So quadric is going to be a generalization in the three-dimensional space of the familiar conics. And in particular, the equations of the spheres and cylinders are going to be examples of quadrics. Other examples of quadrics are going to be the ellipsoid, where this is going to be in general the equation of the ellipsoid. So the numbers a, b, and c in the denominator, if they happen to be all equal, so then the ellipsoid will become a sphere. So the sphere is a particular case of an ellipsoid. So remember then that the ellipsoid, all the terms are adding. We have two types of hyperboloids, of one sheet and of two sheets. So these hyperboloids, if it's one sheet, it looks like this, and if it's two, it's going to have two parts. The surface is going to be disconnected, have two pieces, and it's going to look like that. So the way to distinguish them, you can remember that in the one of one sheet, there is only one term subtracting, and in the one of two sheets are two terms subtracting. More examples of quadrics. We have the elliptic paraboloid that looks like this. I mean, the vertical section will be a parabola here, and the horizontal section will be an ellipse. And so observe that the equation of the elliptic paraboloid, it has all the terms adding, like normally will happen in an ellipse, and there here we have a term of degree 1. In the hyperbolic paraboloid, that is going to look like this, like a saddle surface. So we see that there is a minus, one of the terms is subtracting, and as it normally hyperbola looks like, and the other term as before has degree 1. Observe that this which one has the minus sign will depend on the position of the hyperbolic paraboloid. These are just examples of them. To see what the positions these things are, you need to actually plug in values and see what points belong to this surface and which ones do not. And an elliptic cone, so we have here the one that is called a degenerate surface, where we have the equation equals to 0.